Welcome you all to the other session where we are going to continue our last session related to the programming logic devices. In this session we are going to see programmable logic array and programmable array logic. Coming to the first part, programmable logic array. Now what makes it different from the previous programmable read-only memory is here we are going to have both programmable AND gate and programmable OR array. So two things are there, AND array and OR array. Means I am going to dump my functionality into my AND as well as OR. Now for example, I have taken two functions here, the first function and second function, which I need to implement these two functions onto a PLA. Now my first function is f1 is equal to ab dash plus ac plus a dash bc dash, and f2 is ac plus bc whole dash. So these two functions are to be implemented onto this AND array as well as OR array, producing my total complete logic as a PLA diagram. Now let us see. Now let's distribute my given product terms into product like functions into the product. Now you can see I got three product terms here, 1, 2 and 3, and this got two terms, 1 and 2. Now when I compare these two things, I got one common thing, that is AC and AC. Right? So I can rewrite these two things into one functionality only. So I am writing each product term separately. Now you can see, observe clearly, these are my product terms specified individually for my given functions. Now my first term AB dash, I am mentioned in my table as AB dash, and my product, this is my first product term, and I am representing my AB dash onto my inputs. So I am having A value and B dash value. So I am representing A as 1 and B as 0. And there is no C term, so I am keeping a hyphen here. There is no representation for C. So this AB dash is present under F1. So I am marking F1 as 1. Right? This is the functionality table for my PLA. Next, come to the second product term, AC. So this is my AC. So A and C as second product term. A is present, C is present. I don't have B value, so hyphen for by B value. So this AC is present at two functions. I am having AC product term under F1 function as well as F2 function. So the both functions need to be represented as 1 and 1 at the output level. Next, coming to the third term, BC. So BC is been written here. This is my third product term. So B and C is represented with 1 and 1, and first term A as hyphen. Why? Because I don't have A term, so I am keeping it as a hyphen. So this BC is present under only F2, so I am marking F2 as 1 and F1 as none. Coming to the last term, that is A dash B C dash. So I am marking A dash B C dash, that is as fourth product term, that is 0, 1, 0. Now this product term is present under F1 category, so I am marking F1 as 1. Next, F2 as hyphen. So this is the functionality table for our programmable logic array. Now these inputs are to be mapped onto my logic diagram. Now when you observe this particular logic diagram, I am taking three inputs, A, B and C, along with the inversions. So you can observe, this is A bar and this is A, this is B bar and this is B, this is C bar and this is C. So I got all my three output levels coming from my inputs, three inputs. Now when this is carried out outside, I need to map all the product terms which are present at my functional level. The first term is AB dash. So AB dash has to be mapped with my AND gate. That is, first AND gate should be mapped with AB dash. So this is my AB dash. Second term as AC. So second product term I am mapping to A and C lines. So now you can see this is this line is A and this line is C. So this is the marking that I need to do for each AND gate. Next term is BC. So the BC value is mapped at the output level for AND gate. Next, the last line is A dash B C dash. This is A dash B C dash, which is mapped onto the one more AND gate. So 1, 2, 3 and 4. 4 AND gates got programmed here. Now, after programming my product terms, I need to sum up all those required product terms. So the first F1 function got three values, three product terms. So the three things will be mapped onto my F1 function. So this is F1 function, that is this A dash B C dash AC and AB dash is mapped onto my first OR gate. Second OR gate is mapped with AC and BC, which is giving me F2 function. So this is how we are going to program the given function using a functionality table as well as the logic diagram, where both AND gates are getting programmed and OR gates are also getting programmed. Let's get on to the other version of PLA, that is program array logic. Now the diagram which was represented there, I have represented in terms of functions F1 and F2. Both functions are represented here. F1 has 0, 1, 2, 4, F2 has 0, 5, 6, 7. Now he has given us directly the min terms he has provided us. With the help of min terms, I need to find out two expressions here. F1 function separately I need to find out, F2 function I need to find out separately. So when I am doing K-map with the help of the given min terms, I am getting F1 function as AB plus AC plus BC whole dash. Whereas F2 function I am getting it as A dash C plus A dash B plus AB dash C dash whole. Now based upon these two functionalities, I have drawn this particular table with the help of input lines and output lines. Now these particular terms, whatever I am marked with ones, are the product terms which I found after getting my logical expression using K-map. Now, if you see the functions which we have got opted over there, those functions we have directly mapped here using the functionality table. That functionality table, now you got this particular expression, two expressions we got from K-map. These two expressions we are representing under a PLA table. Now I got all the product terms. You can see AB, AC, BC. AB got repeated, AC got repeated. So that is the reason the number of product terms are less over here. And the two different terms are BC and A dash, B dash, C dash. Those two are also represented here. So I got only 4 terms. Now these are represented based upon inputs and output functions. So inputs, you know, if AB product term is present over here, I need to represent only A value and B value, and C will be kept it as an hyphen. Whereas AB function is present both in F1 and F2. Whereas AC is also present both in F1 as well as F2. BC is present only in F1. So I am marking only F1. A dash, B dash, C is present in under only F2 function. So based upon this functionality, we have drawn this particular diagram. This is A, B, C along with those inverters. Now my first function I need to represent as AB. So I am connecting A line and B line. Next AC, A line and C line. Next BC, B line and C line. Next A dash, B dash, C dash. So I am connecting all A dash, B dash and C dash lines. So I got all the required 4 product terms from AND gates. From this I am connecting 2 OR gates, from where I am connecting F1 function as one output and F2 function as the other output, where I am getting all the inverted operations for them. So this is the diagram for PLA, and according to this thing we can implement the functionality table using AND gates and OR gates. Let's see one more example. Now this is program array logic. The previous thing was program logic array. This is array logic. Now here we are going to implement a full adder circuit. This is a full adder circuit. This table, you know, everyone. Based upon that table we are going to draw this particular diagram. Now using sum expression as well as carry out expression, you know, x dash y dash c, x dash y c dash, x y dash c, or else I can also write this particular expression as x exclusive, y exclusive, c in also. This expression is also going to represent the same thing. And C out, you know, the same thing. For this thing I have brought 3 product terms are there. So x, y and c. So these 3 things I am bringing out all the lines with inverter values. Once inverter values are brought together, I want to map all the product terms. Now this first AND gate is going to represent x dash, y dash and c. So you can see clearly this is x dash, this is y dash and this is c. So this is giving my first product term. Second product term is given by this second gate. Third product term is given by this. Next last product term is given by fourth gate. Now when I am combining all these expressions using an OR gate, I am getting my sum value as my output. For carry out, I got 3 product terms. So 3 product terms I am getting through
first 3 AND gates. So no need of drawing this last diagram, last gate also. With the help of only 3 gates, you can get through an OR gate where I am going to get my C out value. So this is how we are going to implement programmable logic array and program array logic. So based upon this one criteria, we are going to design our circuits. The PLDs which we will discuss, programmable read-only memory, programmable logic array and programmable array logic. Those were the designs, and we were constructed some using full adders, off adders. We constructed PLA, PROM and PAL. So some of the advantages of using program logic devices, like they are reprogrammability. Like once we programmed one device and we utilized its function completely, we can use the same device for any other functionality. So that's the reason we are calling it as a reprogrammability. The second thing, the low design cost, means the cost of hardware which is included in designing this particular PLDs is very low, and less board space. The space occupied by the hardware which is present as a design is requiring the lesser space, and it is faster in the operation. Why? Because we are using only the logic gates in operating our functions, so that's the reason it is faster in, and it is occupying the low power, that is smaller power consumption is taken by our hardware. The last one, it is more reliable, like fewer ICs. ICs stands for integrated circuits. It requires lesser number of connections on board, and availability of design software. The software that we use for connecting the functionalities on board are like Xilinx, Model Sim. Those are the softwares which are the tools which we are going to utilize for designing any kind of logics on board itself, and we are going to check the functionalities on board. Okay, so these are the advantages of programmable logic devices. Thank you.